we don't understand. So this is what I'm hoping to talk about tonight. All right, so let's start at the very beginning. So the question is, what is gravity? All right, so one way to think about gravity is it's simply the weakest of the four fundamental forces. So we have these four fundamental interactions. There's gravity. All right, let me know if this is unclear. There's the electromagnetic force. There's the weak force, and there's the strong force. All right, now the last two of these forces here, the weak force and the strong force, they occur only at atomic distances, and they fall off very rapidly. So that's probably why you're less familiar with the weak force and the strong force. So the strong force is responsible for holding nuclei together. The weak force plays a role in various radioactive decays. The electromagnetic force is a force that you're more familiar with, having to do with charged objects. And then there's gravity. So gravity, we say, is the weakest of these four fundamental interactions. So what do we mean by that? So when we say it's the weakest, we need something to compare it to. All right, so a very simple test that we can do is we can consider the case of, say, two protons. So we have these two subatomic particles, protons. They each have some mass. We can label their mass by some mp. So this proton has mass mp, the other one has mass mp, and they each carry an electric charge, which we can label with E. So electric charge E, electric charge E. And let's assume that these two protons are some distance apart from each other, and we can label this distance by r. Now there are going to be forces that affect these protons. There's going to be a force between them because they both have an electric charge, so they have the same charge. And if you think back to high school physics, you remember that like charges should repel each other. So there's going to be some force between them due to their charge, but there's also going to be a gravitational attraction between these two protons due to the mass that they have. So we can compare the magnitude of these two forces that they have. All right, so let's start with the electrostatic force between them. So for the electrostatic force, we're going to use Coulomb's law, which tells us that the force between these two particles is going to go like the charge squared divided by the distance between them squared. All right, this might look a little bit familiar to some of you. So the greater the charge, the greater the force. The greater the distance, the weaker the force between the two of them. All right, similarly, we can do the same thing with the gravitational force. Let's do that in red. So the gravitational force F between these two instead is going to go like the mass of the protons squared divided by the distance between them squared. So a very similar formula, and let's be a little bit more accurate. We can stick in a proportionality constant that appears in front here, which we label G. This is just known as Newton's constant, and this is telling us really precisely how big the force is relative to this mp squared over r squared. Okay, so what we want to be doing is we want to be comparing the strength of these two forces here, the strength of the electric force and the strength of the gravitational force. So let's take the ratio of these two things. So if I take the ratio of these two guys, I divide one by the other. So this is F Coulomb divided by F gravity. Then something kind of cool happens, which is that the r squared drops out from the top and the bottom, right? I can cancel the r squared in the numerator with the r squared in the denominator. And what I get is something that I can just plug numbers into. So we know the charge of the proton, we know the proton mass, we know G, and so we can calculate what this is. And it turns out that you get something that goes like 10 to the minus 36. So an incredibly small number, right? This is a decimal point with 35 zeros and a 1 at the end of it. So this is telling us the ratio of the electric force between these two protons divided by the gravitational force. So when we talk about gravity being a very weak force, this is what we're talking about. We're saying if we have two protons and we want to compare the electric force with the gravitational force, we have a 36 orders of magnitude difference between these two things. Okay. Other way around. Oh gosh, okay, thank you. Sorry. F grav divided by F Coulomb should give you 10 to the minus 36. Thanks very much. Much better. Okay, so why are we interested in gravity if gravity is so weak? We're interested in gravity because at very large distances, it still becomes the dominant force, right? So we said again, the weak force and the strong force, these are two forces that are really only important at atomic distances are smaller. As we go to larger distances, we do care about electrically charged matter, but as we go to very large distances, say the size of a planet or a solar system or a galaxy or a cluster of galaxy, objects on these sizes are generally electrically neutral. They don't carry electric charge. And so when you don't have electric charge, it's gravity that becomes the dominant force. So gravity is really what we're interested in when we're talking about solar systems or galaxies or the evolution of the universe. So this is the scale at which gravity becomes very interesting. All right, so the key takeaway is that there's this Newtonian law of gravity, which we wrote down, that says that F is equal to